Hello, this is Patrick O'Shaughnessy, and I will be discussing spatial graphing techniques in this module associated with the InTERACCT series. The topic covered in this three-part module is concerned with a graphing technique that can be applied to a set of exposure measurements made spatially within an occupational setting. So part one will discuss spatial graphing in general and then get into the specifics of how to acquire the data needed to ultimately result in a contour map of exposure assessment data. The primary goal of the spatial graphing process is to enhance your communication of hazards to workers and/or management. As such, it is another tool that can be very useful for demonstrating exposures spatially over large areas within a plant, for example. Once the graph has been made, as you will find out, they are easy to interpret and readily allow for an assessment of the hazard relative to the plant floor space. Just about any type of exposure assessment technique can be used to acquire the data to create a spatial graph. For example, aerosol and gas concentrations, as well as even noise readings, so that this technique can be used for different hazard types. Of course, personal and area monitoring can always be performed within a plant, but an advantage of providing a spatial graph of contaminant concentrations or noise readings is that it readily identifies problem areas. It also provides a holistic view of contaminants throughout a plant floor to emphasize differences across areas. If a spatial map is made for concentrations developed, say, in the morning and then one made in the afternoon, then the temporal changes within a plant from morning to afternoon can be highly emphasized with a spatial graphing process that allows for easy visual comparisons between the two. The same is true for comparing improvements, say, after retrofits to control devices. Likewise, you can visualize hotspots of contaminants coming from a source and any other related sources of contaminants. These plots can also display areas where contaminant concentrations are distributed homogeneously or are widely varying across a space. And lastly, spatial graphing can help identify sources of contaminants because of the high concentrations that result in certain areas from a point source or a spatially derived source. So with that introduction, we can now focus on methods to acquire spatial data needed to produce a spatial graph. When considering how to develop the sampling campaign, certainly the primary consideration is associated with having an area sample at various locations. From there, it is a matter of consideration of how many measurement devices of the same type you have available. If there's only a limited number of devices, then in order to accomplish being able to sample at multiple sites throughout a space, either the same device is periodically located throughout the area to be evaluated, or a network of multiple devices is placed throughout the area. In the first case, a measuring device, or a group of devices of different types perhaps, can be put on a cart in order to move them easily from one location to another location. A concern associated with this approach is that while sampling at each location, there is also a temporal change going on in the space at the same time. And I will cover that issue later in this presentation. Certainly the most efficient method is to have enough measuring devices available to put them throughout the space to be measured, so that simultaneous measurements can be made from the devices. If the measurement devices are electronic, that they might also be capable of being tied together via a network of some sort, which would then report data to a single monitoring system for later analysis. However, the devices can always be set up at fixed sampling stations and all turned on at the same time to record concentration conditions over any length of time. A brief sampling run can be conducted to give a spatial graph of conditions over a short but critical time period, or they can be turned on for a longer time to then obtain an average of concentrations over the time to, for example, to obtain a map of morning conditions versus a map of afternoon conditions. When multiple electronic devices are used, however, it is critical that they be co-located before a sampling run to be sure that their response to the same concentration is the same. Either direct reading or time-integrated samplers can be used to create a spatial graph. If it's a direct reading instrument, then we have to consider the sample rate relative to what's going on in the atmosphere of the plant. Typically, concentrations are going to change slowly over time, so the sample rate can be fairly long. There is less data to deal with if a time-integrated instrument is used, and the instrument must be operated long enough to obtain a reliable sample. For example, if measuring particulate matter with a filter, the sampling time must be long enough to acquire a measurable amount of mass on the filter. The time to sample may be over the course of a shift in that case. Now, in terms of sampler placement, ideally, the more locations for the samples to be taken over the space under investigation, the more resolution you can obtain in the contour plots of concentrations that will result from those measurements. So higher numbers of sample locations equals higher resolution. As you can see on the right is a schematic of a scenario in which a floor area has been subdivided into locations in which the sampling cart or the sensor network is placed in evenly spaced increments within the area. Now the space under investigation has been overlaid with a grid of black dots. These are the grid nodes of the map grid that will ultimately be constructed to make the contour plot for the spatial graph. A grid is a set of uniformly spaced nodes that are required for plotting concentration contour plots. There is no software available in which you could have unevenly spaced nodes to create a contour plot. Therefore, if you understand how the grid nodes will be placed over the space, that will help guide the location of the sensors. Certainly, the highest quality plot will occur, and the mathematics of developing the plot will be simplest if the sensor locations match the grid node locations. But that is typically impossible from a practical standpoint of sensor placement and/or sampling time available to sample at each node. As an example, here is a study by Peters et al. Of mapping of ultrafine particle concentration in an engine machining assembly facility. Notice that the sample locations are given in crosses throughout this area. And notice that the sampling locations are not located on a uniformly spaced grid throughout the sampling area. For example, they can be clustered in areas where it is expected that the concentration will change dramatically compared to greater space between them, where the concentration is expected to be more uniform spatially. Notice also on the left, and by way of the color gradations, that the grid square applied during the interpolation procedure can be determined, which is much smaller than the space between the sample locations. So each corner of the square represents a node of the grid map of interpolated values. Likewise, as shown in the spatial mapping, there's a hotspot of concentration that's located in the bottom left, and shown with a red coloration that readily identifies an airborne particle source in that part of the plant, as compared to the light blue areas where very low and uniform concentrations exist. So as alluded to earlier, there's a possible confounding issue of changes in concentration over time while also trying to measure changes over space. This problem occurs when trying to make multiple sequential measurements from a single sensor that is moved from location to location. Obviously, in that case, one measurement is taken at one location and then the sensor is moved to then take another sample. However, during that time, it's possible that temporal changes have occurred, as well as changing the spatial position of the sensor, which might indicate any spatial differences. So there are two possible solutions to this problem, but first, a bit more explanation on this effect is necessary. So to explain a situation in an extreme example, suppose there is a perfectly homogeneous environment over a plant floor space in which the carbon monoxide concentration is exactly the same over the entire space. If you do a sampling campaign in such an environment, then the resulting spatial graph should be all one color to represent the single concentration measured uniformly throughout the plant, as shown here. If, however, the concentration remains spatially uniform, but increases linearly everywhere over time, then by the afternoon, say, the concentration will still be the same everywhere, but at a higher level. Now, for example, if a cart containing sensors is moved around the space in the pattern shown here, and if that increase over time is not considered, then you can see that the very last place measured in the upper right of the space will have a higher concentration than the first place you measured earlier in the day. As a result, the spatial map will show a gradation of concentrations depending on the time during which measurements were taken, perhaps similar to the one shown here, with concentrations that increase from the bottom left to the upper right. Now, Kohler et al. In their paper analyzed this problem and came up with some guidelines that first involve selecting a single sampling location to take measurements for hours, perhaps all day, to determine whether or not there is a significant amount of change over time at one spot. Then the standard deviation is divided by the mean to obtain the coefficient of variation, or the CV value. They then recommend that a CV greater than 0.5 is too high to perform a meaningful spatial mapping process. There's just too much variation across an day or the time period in which the samples were made, and therefore maybe personal exposure assessments should be conducted instead. If the CV is less than 0.5, they split it out between less than 0.1 and greater than 0.1. When less than 0.1, there is little temporal variation and the situation is good for performing a spatial assessment after ensuring adequate spatial resolution. However, if the CV is between 0.1 and 0.5, they suggest prioritizing replicate measurements rather than a spatial mapping process. Another approach to alleviate the problem of temporal variation is to utilize a fixed sensor while you're also moving another sensor around for the spatial measurements. A fixed sensor would indicate the variation over time while you're also taking measurements over space. The measurements made with a fixed sensor can then be used to compensate for temporal variation in the mobile samples. The compensation occurs by applying the ratio of the change in concentration from one time point to another by the fixed sensor to adjust the amount of change in the mobile sensor. To make the adjustment to a mobile sensor reading, therefore, we first define C sub ft as the fixed sensor reading at some time t, and C sub mt is the mobile sensor reading at the same time. The ratio of C sub ft relative to C sub ft when it was started at time 1 is then inverted to correct C sub mt for any change in concentration over time. That approach was taken by Peters et al. When applying the spatial graphing technique to a very large swine building area in Iowa. Here the graphic shows a network of black dots that indicate mobile sampling locations. There were also 5 stationary sampling locations within the building, shown with numbers. The mobile locations closest to a stationary sensor location were compared to that stationary value to modify the mobile sample concentrations relative to any increases or decreases in the stationary sampling locations that were tracking temporal variation over time. To further explain this study, sampling was conducted during 3 different seasons. The resulting spatial graphs showed the highest particle mass concentrations in the winter, when the ventilation rate through the buildings was dramatically lower relative to summer. Likewise, the tunnel ventilation moving from left to right during the winter with a very low flow rate showed relatively uniform concentrations down the length of the building, although high, whereas concentrations were higher on the downstream end of the building in the spring as the ventilation rate increased and moved particles to the right end in a faster fashion. Further increases in ventilation during the summer resulted in high dilution of the particles, which significantly lowered concentrations throughout the building, except, as you can see, a hot spot that happened to be near a door, with particles coming into the building at that point.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies Program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.